let's move on to our discussion first. I think we are done with the beta function 13.3. Now we are in the section 13.4, the Stirling's formula. And it's very useful formula. So I mean, although it's just one very specific property of the gamma function, basically the asymptotic series of the asymptotic expansion for the gamma function. But it's useful enough that I would want to go through that. It's most commonly used in statistical mechanics. Have you used that in your StatMech class? You used that, but you didn't know how it comes from. Basically, it's the approximation of the factorial function for large number, n factorial for large n, and that is very useful in statistical mechanics, and we use the Stirling formula quite often. But it's coming from the gamma function, and the discussion in the textbook use another method to derive that, maybe a more complete method, use a so-called Euler-Maclaurin integration formula, which is one topic in chapter 12, which we skipped. And then within it, it also used another topic in chapter 12, or these Bernoulli number, because that's end up the coefficient of the series will depends on all this Bernoulli number, which we also skipped. And then the derivation is, if you follow the whole derivation, is quite long and complicated, right? So I prefer to use another method to discuss it, which is another topic in chapter 12. It's what we call the steepest descent method. Right, this section 12.7. The reason is that this method applies to many cases, have much wider application than just the discussion of the Stirling formula. So it's very useful. A method like this, I actually use that in my both my master research, or research for my master degree and PhD degree. So it's using something like that, the steepest descent, and there are other name of that. Some people call it the saddle point method. It depends on the situation. A similar method is called the stationary phase method, and the idea is very similar. And so we'll do that. We'll derive that using that method. So basically, there's an example in section 12.7. We'll follow that example. Although the 12.7 first derive a general formula and then apply that formula to the gamma function. And we'll not do that. We don't derive that general formula. We just specifically for the gamma function, we evaluate that using the same idea, but for the particular integral in the gamma function to illustrate the idea. And then obviously, once you know that what the idea is, you can generalize that and then derive that formula for a complex contour integration. And basically integrate over what we call a settle point. Because when you have analytic function, you remember that the analytic function, they don't have the function, the magnitude of the function. There's no maximum or minimum, right, for analytic function over the region that is analytic, right? You hopefully still remember all this. There's no maximum or minimum. So if the derivative is 0, it must be what we call a settle point. So it's maximum at some direction and minimum at other direction. So-called a settle point. We'll talk about a little bit more, but let's continue using the gamma function first. And so we start with the integration formula for the gamma function. remember that the first representation, integration representations, gamma z. This is equation 13.5 equals 0 to infinity. Get a minus t, z minus 1 dz. Right, and there's some restriction on z, but this case is z will z greater than 0. But first of all, to evaluate that, we shift this argument. In many cases, in the textbook, the argument of gamma function or the digamma function, all that we evaluate as z plus 1. We change that to z plus 1, and basically get rid of this minus 1. Okay, so that's the first step. All right, and now to evaluate that, because there's a z in here, we want to basically normalize things using this z parameter. The t is, say, do a change of variable like t is equals to z times rho. Okay, so that is just a change, a simple change of parameter, right? Because we ultimately we want to get a integram of a form exponential function, and with a large parameter. In this case, we try to consider the limit of z goes to infinity. It doesn't have to be that large, but just sufficiently large, because we'll try to get a formula, the asymptotic formula for z, large z. So in that case, we try to make the exponential function has a large parameter multiplied by another function of the integration variable, right? And in that case, there's exponential function, and then if we scale t with z times rho, using rho as your integration variable, then you have explicit z out in front of the argument of the exponential function. So that's the idea why we do that change of variable. Okay. In that case, about dt, that's why I'm confusing. Okay. All right. Now, so let's just write out explicitly. So infinity t is exponential minus z times rho, and t is z rho, and then the power z, right? And dt is ct. Okay, and rho is still going from 0 to infinity because it's just proportional to z. And rho is, I mean, t is 0, this is 0, t is infinity, this is also infinity. Okay, so and then another trick is the formula required that to write everything as an exponential function of an argument. And so there's a rho to the power z. We want to write it as an exponential function. So what we do is just rewriting rho times z as exponential function of log rho times to the power z. Right, that's just redundant. The exponential of log will get back the same function, right? But then in this case, log rho to the power z is just exponential function, right? Log rho to the power z is z times log rho. Is okay? So that now you get this factor also as the exponential function to some argument. Okay, and now we can first take all those rare factor that is not dependent on rho not depends on the integration parameter. So that's we don't need that in the integral. So it's c to the power z, and then there is also an extra factor. And here is the z minus 1, right? Plus 1, yeah, not much. This is in the z to the power z times 1, right? All right, and I think that's it. And then 0 to infinity, exponential function. And there's a z in front. And then there's a log rho. And the minus rho. And 0. It's okay. So you just basically transform your original integral to here, this form. Is it okay? Up to here. Right? And that is actually another technique that is very commonly used. So whenever you see integral, you normalize it nicely or by reasonably try to normalize it. And once you normalize that, you actually get the dependency of the function already. The major dependency of the function. In that case, is z to the power z plus 1. Right? That is all. You already know without doing anything about the integral. You already know that it depends on that functional form, and which is very powerful already. Because remember that that is almost all the majority of the Stirling formula. The Stirling formula usually is writing as in fact, it's logarithmic function. So instead of n factorial, usually writing as log n factorial. Remember that. That you already get the majority of that formula with this factor. So, and the integral give you something else, but this something else is actually what we call the order of unity, right? And you see that by considering this integral, right? And which we'll need to do for this steepest descent method. Okay, so look at this integral is exponential function of a large parameter multiplied by a function of this integral variable. So you need to look at this function, right? And this is log rho minus rho. If we consider the domain of integration, this rho is 0 to infinity, right? At rho goes to 0, log rho is negative infinity, right? Yeah, so it's just this factor is negative infinity, right? And then at rho goes to not yeah, negative infinity, that's fine. And then at rho equals to infinity, when rho tends to infinity, log rho is going to infinity, but it's going to infinity slower than rho. Rho is going to infinity, so it's going to minus infinity, and then it's there's an inverse power. So inverse power. So, and you don't know something inside within whether it caused the positive the zero line or not. That needs more analysis, but the asymptotic behavior of this function at the two limits 0 to infinity, you know that both are going to negative infinity, and you have an exponential function multiplied by z, and with this formula we divide by positive z, right? And later on you can do analytic continuation to generalize to compact z, but that's the second step. But for first step, we consider the positive z. For positive z, then negative infinity, exponential negative infinity times a large positive number, then the integral is 0, right, at both ends. So you look at the integral. So this is this factor, but the integral just now another function would be 0 in here, 0 in here, and then because it's exponential function over a large parameter z, so it will be a very steep, very highly peak function somewhere, and this is where we wanted to determine what is this what is the location where this the integral is maximum. And obviously, this maximum is when the argument is, in this case, is largest, because it goes negative infinity at both ends. When this function, log rho minus rho, is the largest, and obviously this argument, the whole integral is peak at this peak. So exponential z times this part, right? And exponential of that argument will have a peak, right? So you want to determine where the peak obviously when this is maximum. So we need to determine this function log rho minus rho, the maximum of this function, and let's call this f. F is log rho minus rho. Okay, and to determine the maximum, we take the derivative. df d rho equals to 1 over rho minus 1, right? And set this to 0. So rho is equals to 1. And that is, supposedly this should be the maximum by this behavior, but we can confirm that is a maximum by taking the second derivative, right? Now the second derivative is d square f d rho square. That's, in this case, it's just simply minus 1 over rho square, right? It's negative because this is rho square minus the positive number, so it's negative. And negative means maximum, right? So you still remember your calculus, right? So this has a maximum at rho equals to 1. And what is the value of f at rho equals to 1? So f1 is 1 is 0. The first term is 0. The second term is minus 1. So it doesn't cross the real axis. Not the real axis, the 0 axis. So this is the function. This is 1, right? And this is minus 1, right? That's the part of this the argument. This part, and the whole integral is exponential of this 1 times z, and so it's highly peak, and it's very peak. More peak if z is large, it's more and more peak. If z is really large, then you can see that we go to very large value, and then it's dropped down. It's highly peak function. Is okay? So that's the property of this integral. Is okay up to here? And that is why we call it the saddle point method, because we try to find a maximum or extremum. In this case, extremum, and but this is along the real axis, so it's you just consider whether it's maximum or minimum. But if you have going back to the general discussion in section 12.17, so you have a complex z-plane. Now it's not this z, it's a general integration. So you have a complex contour z, right? And of some function, exponential of some function, not just like this, but it's a complex function. What we try say like the integral is the exponential function z f z or zft in this case, or maybe not because I have the same z here, z of let's just create what do we call it, m or something like that. M is large, okay, right? So that is a parameter, and then this is a complex integration along z, right? And you want to find the location where df dz is 0. But if f is an analytic function, we already talked about that. That's somewhere here you have a df D is 0. And that location is not a global maximum or minimum, meaning over all direction. It's actually what we call a saddle point. Your textbook actually in the 12.7 has a picture. So if you draw it in the two, if the 2D plane, 2D Z plane is something like that. So this is this Z plane. Just plot this max F value as a surface part. So somewhere at this location when you have maximum, then this function will be at the maximum as over some direction, but then it's a minimum over some other direction, right? And that is what we call a saddle point, right? So it's kind of hard to draw a surface on the blackboard, but you can look at your textbook that figure. And the idea of the saddle point method is that we try to cause the saddle point when it's over, when it's over a minimum. So if along this side has a maximum, we try to use this cause this over the maximum. The direction when the function is maximum, we try to avoid those hills, so-called the hill. We just try to go over, just like this function, we try to cause it over the maximum. So we choose, we can deform our contour such that it cause the saddle point over when it's over this is called, this is the hill, this is like the valley. You go just like when you have a highway, you want to go past the mountain, you try to cause the point where you don't want to go up the mountain, go up the hill. You just want to find the valley and then go past it. Although you must cause this point, but you just try to get basically as minimal effort as possible. So you want to cause it that way. In that case, you can draw the saddle point. Say this two direction is the hill, the value, and this two are the map. The hill that's going up. This two the function going up. This two the function going down, and you try to cause the saddle point this way, and this determination will determine the direction of your angle of this path C over the saddle point, and that define a function, whatever this function is, angle phi or something like that. That's in the discussion of section 12.7. That would give you a phase in your integration, right? But we're not consider that here, right here, because we have a integration along the wheel axis, so that's we don't need to consider the saddle point because we have to go through the wheel axis, and as it turns out, along the wheel axis, the function is maximal already. Okay, so we are basically causing the saddle point over the maximum, not the minimum. Okay, so that's the consideration. Now, with that, we can continue this evaluation. Okay, with that, so start from here, continue to here. What we want to do is do a Taylor expansion of the arguments of Z. This is what we call F, right? What we want to do is F at the F around the saddle point. Or this is a function of rho, right? So let's call this rho max, rho sub m. Okay, basically F at rho sub m plus F df d rho that evaluate at rho sub m, rho minus rho m, and plus 1/2 d squared f d rho square evaluate the rho sub m rho minus rho m square. And then there are other terms, but we ignore those for this method. We just expand this part in Taylor expansion up to second order. Okay, and then d rho. Okay, so that's what we'll do. And now we just need to plug in the number. And the first thing is already trivial, is dfd rho, because by choice at rho sub m dfd d rho, we choose it to be 0. Right? And now f rho sub n is f1 is -1, so there's a -1 here. Okay, when it's -1, it's not depends on rho, so we can take that out. Z plus 1, and you have e to the minus z. That part can go out. Okay, and the other part is just 1/2 of the second derivative is -1 over rho square, and evaluate rho sub m, which is 1, right? So it's -1. So this one is simply -1, right? It's okay. So that is an exponential function -1/2 of this rho minus rho sub m square. It's okay. I forget the z. That is important. Right? And now come the approximation, because up to here is just the Taylor expansion. It's also an approximation, but to evaluate that, we are using the fact that it's highly peak for a large z, and then so this is your rho sub m is 1. Right? So the whole thing fall to 0, just very shortly to the left and right of rho sub m. So it goes to 0. It's very small. So basically, it's like a Gaussian integral. We're already taking most of the Gaussian integral over this whole range. So we can just say that this whole thing is just a Gaussian integral with so this is approximately z plus 1 and minus z. You can just say that this is a Gaussian integral. And this is your new parameter. So it's z e to the minus z over 2 like z squared. Right? Using this, because c is rho minus rho m. But it's already like move integrating from net minus infinity to infinity, because you're already taking the large part of this Gaussian function already. You can just approximate, just integrate the whole range, because you want the whole range, because that the closed form for that. If this is still a function of some variable, then you get the what you call the error function. You don't want to get to that much complication. You just approximate like a full Gaussian integration. Now this one, you basically just need to normalize that. So normalize that to a true square function. So you multiply by square of d over 2 and divided by square over t divided by the whole thing and divided by over c. Right? And this whole thing, it's just a Gaussian integral. It's square root of pi, right? The whole thing is it square root of pi? I think so, right? Yeah, the Gaussian integration. So this one is square root of pi. So combine if everything. So this is you have this, like write this first 2 and square root of pi is 2 pi here, and then you have a z here, and then z plus 1 exponential minus z. And if you like, you can just combine this c in the denominator 1/2 factor, 1/2 power into this z function. So right, like square of 2 pi t to the z plus 1/2 e to the minus z. I hope I got everything correct. Okay, see if I got everything correct. That would be the final formula if I got it correct. And that would be to, well, need to go to section 4. This is to compare with the other formula, the other derivation. So this is, there's no equation number. Basically, the equation after 13.60, that, right? And, or if you take the log, so this is the gamma function. This is this one, right? Gamma function c plus 1 is approximately given by that. That's the one form of the Stirling formula. And using the steepest descent method, we get up to this, all this factor. If you use the textbook's method, there will be some other term, and we can write as a log. So if we take the log of gamma c plus 1, so the Stirling formula is just basically taking the log of this. Now, the log of that, you can do it in the order of from the largest factor to the largest term to the smallest term. The largest term, obviously, is coming from z to the power z. Z to the power z, obviously, is the largest one. Largest term. And when you take the log, becomes z times log z. Right? That's the largest factor, and becomes the largest term in the logarithmic function. The next one is z to the 1/2 factor, obviously, right? Z to the 1/2 factor, when you take the log, is 1/2 of log z. Right. And then there's another term that which might be, we should actually put that first, because that actually is of high, although this is an exponential function, but there's a negative sign. We take the log as minus z. Right, that is the, this is z, this is of the order of z log z, this is the order of z. That is coming from the exponential factor. Now come the next order is this z to the 1/2, which is 1/2 of log z. And finally is this constant, that's log of square root 2 pi. Right, and this formula means some other terms, right? And this is to compare with the final formula is 13.60 using the Euler-Maclaurin integration formula. So compare with that, this get all the terms. So that formula is z log c. You have a minus z. You have the 1/2 of log c, and then log of 2 pi. I mean, you can take the square as 1/2 factor, it doesn't matter. And then what is missing are all this term is inverse power of z, inverse of z, 1 over z, or 1 over z cubed, 1 over z cubed. So all these terms in this log formula will go to 0 as z goes to infinity. Right? And so we keep this method, the steepest descent method, can get you all the terms up to those terms that will stay finite as z goes to infinity, and all the other terms will go to 0 at the asymptotic limit. Although the asymptotic expansion is a divergent series, that's another section in chapter 12. So, but you can evaluate a asymptotic series as as for large z up to, if you have a series, you just evaluate up to when the series start to increase, so we would all these terms, you keep evaluating all the terms. Those terms will be getting smaller and smaller, and then we'll somewhere along the line, depends on what the value of z it will go back up. It will go increasing again. So you stop your summation at that point, and that will give you a good approximation. Okay, and but for us, most likely you will just use all this term, and even for statistical mechanics, usually just keep these two terms, right? If you remember, so this is like a z factorial. If z is a integer, this is z factorial. So like n factorial is n times log n minus n. So that's the usual Stirling formula that we use in statistical mechanics up to this term. And we don't even keep these two terms for very large n, for large z. Okay. So so therefore this method is still very useful. Although we're missing all these other terms, but it's okay, at least for the same formula, because most likely will apply to the case with a large z anyway. All right, is it okay? This derivation, can you follow that? Most, I mean, I go through that just to illustrate this method, because the method itself may be even more important than the formula. The formula, you can look that up and you can apply that just by applying the formula, plug in the formula. But the method for any unknown integral that has some of these forms, e to the z times some function, and if z is large, then you can consider using this this method, the steepest descent method, and get the approximate value out. Is that okay? So that's 13.4.